Okay, so we have the second part for the video, and this time I want to show you some applications about modular congruence. Now, what are the applications? So number one is this. So we can use modular congruence to find remainder. So remainder is the remainder you got when you perform long division. So how do we get the remainder? Well, so you have to do a very short recall about long division. So notice that for positive integer, say a and b, okay, a and b, a and b, okay. Now if you have a strictly bigger than b, then by long division, or you say by division, okay, you always have a, for example, a equals to b times q plus r. Okay, you just divide the smaller, the larger integer by the smaller integer, then you have the quotient q and the remainder r. Okay, and for some integer q, okay, as well as you have a integers q and r with 0 uh, less than or equal to r, but strictly less than b. Okay, so that is the definition about the remainder. Okay, now if you look at this equation, a equal to bq plus r, in fact, using congruence, okay, so using modular congruence, actually you have a congruence to r. Okay, and now modulo what integer modulo b. Okay, so that means if you divide some numbers by integer b, a positive integer b, okay, then the remainder is nothing but just after you take the congruence modulo b. Okay, but you have to remember the remainder must be between 0 and b. Okay, it can be 0, but it must be strictly less than b. Okay, so this is the definition. So now if you look at this, in fact, this is exactly what you want. Okay, when you want to find the remainder between, when one integer is divided by the other one, well, you just have to take congruence. Okay, so hence to find the remainder r, we just need to find integer r such that a congruence to r modulo b. Okay, with you must make sure that you satisfy that equation. So that relation. So r must be bigger than or equal to 0, but it has to be strictly less than b. Okay, so once you can find that integer r, this is exactly the remainder. So let me show you some example. Okay, for example, now find the remainder when 11 to the power 30. Okay, 11 to the power 30 is divided by 5. Okay, now how do you know the remainder? Okay, now 11 to the power 30 is a huge number, so you cannot use your calculator to find the remainder. It doesn't work. Okay, so you have to use the new method. So let me show you how. Okay, so notice that, okay, now you have to see. Okay, so the key for the problem is to reduce the value. Reduce what value? Reduce the value for 11 to the power 30 by taking congruence. This is a very useful method in order to get the remainder, because the original number is too big. Okay, So if you cannot do that, there's no way you can get the remainder. So now first, you observe that 11 is in fact congruent to 1, okay, modulo 5, okay. Now why modulo 5? Because you are dividing numbers by 5, so you have to take the congruence with respect to 5. So 11 is congruent to 1 modulo 5, and hence you get, now you use property 4, okay, so by property 4, okay, property 4, we have, you take power, so you can raise it to any power, is especially you take power 30. So 11 to the power 30 is still congruent to 1 to the power 30, okay, and modulo 5, right? So now, what is it? Now, since 1 to the power 30, actually 1 to any power must be equal to 1. And so, in fact, you just got 11 to the power 30 congruent to 1 modulo 5. And now 1 is what? So since 1 is less than or equal to, 0 is less than or equal to 1, but of course it's less than 5. So it's just within the range, okay? So the remainder is 1, okay? So this is how you apply the modular congruence to find remainder when one number is divided by the other number. So usually the number which is divided is very big, okay? You just apply that method, then you can reduce it using congruence to some very small numbers. I shouldn't say it's very small, but much smaller. Again, much smaller numbers, okay? So this is one example. Now let me show you another one, okay? For example, now find the remainder. Find the remainder when 7 to the power 60, okay? 7 to the power 60 is divided by 10, okay, for example. Now, if you want to find the remainder, then how can you do that? Now, let's just do it. Now, notice that you have, well, actually this problem, okay, so it's a little bit different from the previous problem because the previous one is quite easy because you know 11 is already congruent to 1, then you can take the congruence modulo 5, then once you raise it to any power, it's still equal to 1. But for this problem, it's not that trivial because it's not that easy for you to get the 1. Okay. Now, for example, now you get, now 7, of course, is congruent to itself. Okay, modulo 10, right? Because if you take the difference, 7 minus 7 is 0. So 0, of course, is a multiple of 10 because you can take 0 times 10. Okay? But that's not enough because it's not useful because you want to take 7 to the power 60, right? But before you go to 60, you just try to take some powers and observe the pattern. Okay, the pattern is very, very important for this type of problem. So you have this, and also you have 7 to the power 2, for example. Now 7 to the power 2 is not too horrible. You still know the value. It's just 49, right? But 49 is pretty big, okay? You can take congruence to reduce the value. If you take congruence 10, then you will just get back 9, okay? So that means 7 to the power 2 is just congruent to 9 modulo 10. Okay, so you have it. Now, what next? Also, you can take 7 to the power 3, but my suggestion is you don't really have to multiply 7 by 3 times because you're taking congruence. So in fact, it is just congruent to 7 times 9, okay? Modulo Now why? Because you just split 7 to the power 3 just into 7 square times 7. But 7 square, you just know it. It's just congruence to 9. Okay, so that means you can change 7 squared to just 9 after you take the congruence modulo 10. Okay, so you have this. Okay, but that's not enough, because you can do a few more steps. For example, you can multiply 7 to 9, you get 63. Okay, now 63, you can take congruence. Okay, and then if you take congruence 10, then you will get back 3. Okay, so that means after you take the congruence, 7 to the power 3 is just equal to 3. But still you don't get 1, because now actually one of your goal is to reduce the value as small as possible. Now 3 is not very horrible, but imagine that you still have to take several powers, so that will make the value very big, even though it's just 3. I mean, if the base is equal to 3, then imagine 3 to the power 60 is still a huge number. Now, the only thing you need to do is to try to find some power such that the power give you 1. Okay. Now, it's very close because, okay, therefore, if you take one more time, I mean 7 to the power 4, let's see what is it. As I said, you don't have to multiply 7 by 4 times, because you know that 7 to the power 4 is just 7 to the power 3 times 7. So that would be congruence to 3 times 7. Now why 3? Because you know 7 to the power 3 is just congruent to 3. So you change part of it to just 3. So then you get 3 times 7. And now that number is 21. Okay? So if you take congruence 10, modulo 10, 21 is exactly congruence to 1. Therefore, 7 to the power 4 is just congruence to 1, modulo 10. Now, why so useful? Because that tells you something, right? Because now imagine, what is 7 to the power, now observe that. Now 7 to the power 8, what is it? Now remember, you have some index laws, okay? So 7 to the power 8, you can split the index. For example, you can change it to 7 to the power, 7 to the power 2 times 4, I mean, right? Now if you use the index law, this is exactly 7 to the power 4, and then you take the whole number to the power 2, right? This is the index law allows you to do that. Okay, 7 to the power 4, and then you take the whole integer to the power 2, which is exactly 7 to the power 8. Okay, so maybe I just write down the index law. Okay, so index law. So for example, you have a to the power m times n. In fact, you can always split it. Okay, like a to the power m, and then you take the bracket, and then to the power n. Or if you don't like the order, you can switch the order. So you can switch the order to be like this. They're the same. This is called the index law. Okay. Now you get this. Okay. Now but go back here. Okay. Now you know this is exactly 7 to the power 4, and then you raise it to the power 2. But 7 to the power 4, after you take the congruence, is just 1. Okay, to the power 2, this is modulo 10. Okay, and so because 1 to any power is just 1, so it must be equal to 1 modulo 10 as well. So you just show that 7 to the power 8 is also congruence to 1 modulo 10. In fact, you can see that, in fact, no matter how many power, okay, I mean, if you have 7 to the power 4m, okay, 4 times m, then in fact you can always use the index law to change it to just 7 to the power 4, and then you raise it to the power m, right? You split the product, the product on the index. So now 7 to the power 4, you know it must be congruent to 1, so equal to 1 to the power m, but that is just congruent to 1 modulo 10. So you have this relation. Okay, so no matter how many power you take, you will get it. Okay, provided that the index is a multiple of 4. Okay, hence now 7 to the power 60. Okay, because you can change it to 7 to the power 15 times 4, right? But then you can split the index again, just like what I did, into this 7 to the power 4, and then you raise it to the power 15, and that must be congruent to 1 modulo 10. And so now you have to answer the question, because the question asks you to find the remainder. Even though you show me many steps, show me many workings, but if you didn't show me the answer, of course, I couldn't give you full credit. So the remainder is 1. Okay, so you have to answer the question. Okay, so we prove it. Now, actually, this example is very useful in the sense that now we find the remainder, of course, but in fact it also tells you something. Okay, now you see that to some power equal to 1. Okay, the value 7 to the power 7 to the power 7 to the power 4 is equals to 1. Now actually it's sort of like a cycle. Okay, why is like a cycle? So let me just maybe give you a remark. Okay, now for example, okay, now observe that for example, for any positive integer m, okay, in fact we have this, okay, 7 to the power 4m plus 1. Okay, let's just do 4m plus 1. Okay, now what is it? Well, now it's just index law again. Okay, so you don't have to do any congruence. You just split the index. So 7 to the power 4m, that is, okay, you multiply this number to another number, which is 7 to the power 1. Okay, because you can split the index. If you have a sum, then you can split it into a product. Okay, then again 7 to the power 4m, that is 1. So that gives you just this 7 to the power 1, it's just 7. Okay, so that means that will give you 7 after you take the congruence modulo 10. Okay, so that means if you have a power which is in the form 4m plus 1, then after you take the congruence, it always gives you back 7. Okay, modulo 10. Now you can do a similar computation. Sorry. But this time, let's try 4m plus 2. Okay, and see what happens. Now 4m plus 2. Okay, now same index law, but now you have 7 to the power 2. Okay, now 7 to the power 2, remember, after you take the congruence, is just 9. Okay, so everything now changed to 9. Okay, in fact, this is the pattern. Okay, so it's just exactly 7 to the power 2. So the 4m part just not very important, because it's just congruent to 1. Okay, so this is the property. Now let's have another one. So for example, we have 4m plus 3. Then what happened? Now same index law applies, and you have 7 to the power 3, but this time 7 to the power 3 gives you this, right? 7 to the power, sorry, not this one. 7 to the power 3 give you congruence 3. So that's why you have this. Okay, so this is exactly what you got. Now finally, if you have 4m to the 7 to the power 4m plus 4, then what is it? Now because, well, actually if you have that observation, you can simply take that to be 4 times n plus 1. Okay, anyway, so you have this. In fact, after you take the congruence, they both equal to 1. So you got this. So it's like a pattern: 7, 9, 3, 1, and then if you do another power, you get 7, 9, 3, 1 again. So you just repeat the same pattern again and again. So now the key for the problem is whether you can find the pattern or not. If you can find the pattern, then you solve the problem. Okay.